Hey, come check out our next show on Orleans with Sergey. It's on distributed computing. Take a look. Welcome to another episode of the On.NET Show. Today we're going to be talking with Sergey about Orleans, and I'm Rich. Okay, yeah. So how about you quickly introduce yourself, and then we'll get into the topic.
Sergey Bykov. I've been working at Orleans for many years now, and kind of through the whole story of getting it open source and moving forward. So always happy to talk about it.
Yeah, and we actually kind of worked on the open sourcing a little bit together.
Yeah, we learned a lot from you guys.
Yeah, we went a little bit before, and yeah, that was fun.
Oh, it was more than fun, because when we started talking, I was shocked, like all this energy was kind of, people were glowing out, we're open source. And like, don't do sync from the back end, just do development in the open. That's what we learned from you guys.
Yeah, and we're still doing it. It's super successful. Actually, on that note, I know with our project .NET Core that I'm amazed actually at the number of community developers that are working on the project. Have you guys had any success with attracting folks like that?
Yeah, so we have a very great community. So we have the number of contributors both on the issue side and the pull requests. And like I keep mentioning this guy Dmitry, we merged over 100 of his pull requests.
Oh my
and
gosh.
he focused on performance. So we counted just through his pull request alone, we double our throughput.
Okay.
Speaking of performance.
Yeah, that's super important. We have somewhat similar things on our project.
Oh, you have Ben.
Yeah, we have Ben. And presumably, Ben's performance improvements probably help you guys in some way.
Of course.
So how about we talk about what Orleans is and what it's for? And also, I just recently talked to Aaron at Akka.net, so it'd be good at some point to describe any similarities or differences there.
Okay, so how do we explain Orleans in a couple of minutes?
Yeah, a couple of minutes.
That's challenging. Let's try. So it all starts with kind of good old days where it was client server. Server was holding a bunch of objects with state, and everything was consistent, easy to manage, logs. This whole model fell apart many years ago, probably like 20 years ago when the web started. Because the moment you had the second server, you have two copies of the world and they have nothing in common. There is no coordination. And so the world switched to stateless, where you have front end, stateless business logic. They all talk to storage. Storage is where everything is happening, really. And it's inefficient because you need to read data for a request, right? You have conflicts. Requests come to different servers. So at the end of the day, you overload your storage.
That's bad.
Yeah. And of course, we threw in cache, say, hey, we're going to read from cache, write directly, and then you inherited this problem of cache invalidation and everything. So you deal with two storages. So the Orleans model is based on this idea that let's put a stateful middle tier, which is a cluster of servers, have this virtual memory space, essentially, where these objects will live as if they're in a single server. So like all these limitations of a single server machine, where limited memory, doesn't scale, they all go away if we move to the cluster model. And if something fails, that's handled automatically.
Now, does it become more expensive? Like the nice thing about the first slide that you have, the stateful model, is although it has a bunch of drawbacks, the expense of the system relates almost exactly to the storage and throughput you need. Is that correct?
Yes, that's good.
Yeah, so with this system, is it like, oh, well, I need 3x the cost to maintain this system, or is that not fair?
No, that's not fair. I think it's more expensive because you need to have communication between nodes, and you need serialization and overhead of messaging. But you don't have to multiply. You can still have, let's say, 10 times the throughput if you have 10 servers and a double number of servers.
I see.
That's the idea. So the picture we arrive to is like this. So you have a cluster where you have many these independent objects. We call them grains in Orleans that live, they isolated, and they talk to each other still. But because they're isolated, Now we don't care if they live on the same server or on different servers. So from the user's developer perspective, it's the same. So you have this kind of illusion of a single machine, but you program against the cluster.
Okay. Makes sense.
All right, and I can quickly show code. So like the grain starts with the grain interface, which declares what kind of methods you expose. They all have to be async, and because of async await TPL, we benefit from all of that. The requirement is all calls to grains, these objects, are asynchronous.
Right. So is there some kind of a factory method somewhere which is like, get me a grain of this type?
Yep, that's exactly the next thing. So how do you call a grain? You say, give me a grain that implements this interface with this identity. And that identity is meant to be application specific and stable. Like for user, it could be email, it could be social security number, or phone number. So you say, give me a reference for this grain, which in fact is just a proxy object. And then you can immediately make a call to that object.
Right. So I see that when you get a new grain, that is a synchronous call, so that they're always immediately available for new grains. And then the operations are the thing that are async. Are there cases where you can kind of let a grain rest and then get it back, and then that would be an async call if it's like currently residing on one of those other servers, or that's the wrong way to think of it?
I think it'll be clear in the next step. So implementation is simple, right? Just the class that implements the interface, everything is synchronous. The key thing here is that it's single-threaded. So you don't have to protect this counter in this example. You can increment it and guarantee no conflicts there.
Makes sense. That's more like just the way async works.
Right. No, it's a guarantee. So the say hello will never be invoked on two threads in parallel for the same object.
I see. So even if you do task.run, for example, in there, will that not run on another thread, or you're not allowed to do something like task.run?
You can do different tasks. Task.run is an exception. It doesn't respect.
Okay.
But there is a way to run multiple tasks. The key is they will never run on parallel threads. Within the context of a single object, single grain, they will always be serialized so that one at a time.
Okay.
But so the key here is that this grain it's a logical construct. So it has this identity, like say user email or phone number, and logically it lives forever. So you can always call at any point. You don't need to create. You don't need to delete. You just say, give me a reference, make a call. The grain may not be anywhere in memory. It can be just have persistent state in storage, but the runtime will create an instance of it when needed, execute all the calls, wait for it to be unused for a set period of time, and then removed from memory because it's idle.
I see. So what I understand from that is the grain doesn't really persist over time in the sense of after it's unused, the fact that you might get the same one again is not super meaningful. It's the data that it represents that is the more meaningful part. Is that fair?
Yes and no. The state is the most important part, but also the runtime creates this we call them activation instance in memory in the cluster somewhere, like a single instance. The routes all request for the single like user grain to the same physical object. So you have both persistent state and in memory state, which you can keep there for a long time, and that contributes to low latency and high throughput because you don't have to go to storage for every request anymore.
Okay.
And you get more for that because this grain can talk to another grain, which is in memory. You don't have to go to storage. It's very, very efficient in that sense.
Okay, makes sense.
So we end up with this cluster that actually handles a sliding window of grains.
I see.
Which gives you free resource management. You only have memory used for these grains that are used right now or were used recently. You want to keep them kind of warm in memory. But other than that, you don't have to have resources. You don't have to put all your state for all your users in memory.
I see. So in the storage world, we talk about like sparse allocation of drives. It kind of feels like this is a sparse allocation in the sense that the entire universe that you might be trying to represent might have, a million grains or actors in it, but there's only like 10,000 that are currently active.
Mm-hmm.
And so, but you still represent the case that this million or the other, whatever, 990,000, that they exist. They haven't been deleted in any sense. Yeah.
They all exist the whole time. So that's why we call them virtual actors, like virtual memory. State is in page file, kind of equivalent, but you can always touch this memory.
That's a good analogy.
And this is actually the difference with, you mentioned Akka.NET, so like Akka or Erlang, those call them traditional actor models. There you explicitly create every actor. So you would create user actor X, and then usually you need to pick a server where it needs to live. And then that actor may create another actor, and then you need to remove them from memory. So this whole resource management is on you as a developer.
I see, so more explicit.
It's more explicit, it's more work, it's more space to make mistakes, because if something failed, you have to recover. And here, in this model, without any change, like if say a server dies, right, in this picture, that's a totally normal event, because the runtime knows, oh, we lost actors that are there. We can immediately recreate them on another server.
Right, as long as their state was persisted to a database of some kind, then you're good to go.
Yes, the key is that you don't need to write any application code to recover, to react to a server failure event. You just write code for this class that gets activated, can persist its state, can do some actions, and that's it.
So we saw what that code kind of looked like for grain. I think it was just doing console write line there. But presumably there's like reads and writes to storage. Mm-hmm. Now, do those go through some kind of a layer in between the grain and the database? Or as the grain developer, I completely own, writing to the database and the consistency model that I need?
Both choices are available. So you can go through this kind of simplistic declarative persistence where I say, this is the property back class, and this is the state of my grain. And then we have a notion of providers, persistence providers. You declaratively associate, say, user grain class with, say, Cosmos DB as a provider, or Azure Table, or whatever. MongoDB. And then you just say, write state, you update these properties in the property back, call a single method, and it persists. But if that's not enough for you, if you want to be more advanced, you want to load partial state and handle it, you can just write any code and talk to storage yourself.
Okay, so a lot of flexibility.
Yeah.
Okay. So how about we talk a little bit about where Orleans is currently used today?
In terms of spaces?
Well, I guess you and I talked about this a little bit earlier, which is in computing today, the kind of main cases are desktop, mobile, server cloud, and IoT. So in which ones of those do you see Orleans, where is its sweet spot?
Well, it's definitely the back end, the server side, cloud. Cloud is the natural place, but anywhere on the back end.
Yeah, I mean, from this picture you showed, it's clear that elasticity of resources is a key point, both from the standpoint of scaling out, but also from the standpoint of failure and recovery. And pretty much all the other computing mediums I mentioned don't have those characteristics.
Right, and then from the beginning, when we started Orleans back in research, the goal was the cloud, because it was coming. And that's where you have these failures at the scale that kind of guaranteed, and you be elastic.
Makes sense. So I know from having talked to you before that one of the big high-profile users of Orleans is the Halo service. I think it's been using it for 5 years or something like that, or maybe even longer?
6. So, yeah, more than 6.
Yeah, okay. And has that been a success? Are they still happy with it?
Absolutely happy. And sort of they infected other people because, if it works for Halo, which is a bigger scale than mine, then I should be fine with it. So it was a huge kind of proof point for us.
Right. So is it the case that or I shouldn't put words in your mouth. What in a short number of yeah, how would you describe like why it is that the folks at Halo are happy with that? Like, what's the specific problem it solves for them?
There are 2 points. We touched on scalability, and that was one of the 2 main goals. But the other main goal was developer productivity. So because you don't have to write code to do a lot of these things like handle failures, or for example, we propagate exception through distributed call chains. So you can write try catch as if things happen locally. As a result, you don't need to write code to deliver failures and make mistakes there and debug. So developer productivity is much higher. And some people say they write 3 times less code. Some people claim that 10 times less code. I don't know what the true metric is.
Somewhere between 3 and 10.
That's my feeling. So that contributes to efficiency of developers' work, but also the less code you write, the fewer bugs you introduce.
Absolutely. So it's used in some big services of Microsoft. Has it also been adopted in the outside world?
Yes, of course. So we had public preview in 2014, I believe, and then we open source in January 2015. And like very wide range of applications, some things that we wouldn't even think about. One of my favorite projects is this energy management system in Hawaii, where they have a lot of green power during the day and it distributed to these ceramic water heaters. So they turn them on and off on the very short notice using the system, right, in Orleans to consume and drive excess energy and store it in this form. So everyone thinks like we need a battery. Well, you have a heat battery,
yes.
And then you heat water for free. So that's a fascinating project. Another one was like a couple million mouse traps, IoT. Send a signal that there is a mouse in the mouse trap.
Oh, literally.
Literally.
Mouse traps.
Yeah.
What is it though about, I can kind of grasp the mouse trap one. What is it about Orleans that aligns with this energy transfer story?
The way, can I explain it as, for Orleans shines when you have lots of contexts. And the context may be like a user, session, device. So you have these water heaters that spread around. They have their own properties. Like,
I see.
and you send requests to that specific context and say, turn on, turn off, give me your state. And because it's in memory, you have kind of, for in IoT, they call it's a ghost device. I forgot what the term is. So it's sort of reflection of a device in the cloud, in memory, which has a copy of the state. You can be very low latency and execute very low latency operations with that.
Yeah. I don't think anyone actually does this, but with those kind of systems, I always think of, it's like, buy power during the night and then pump water behind the dam with that cheap power and then run the turbines during the day and sell higher price power.
Kind of the same
it's
in reverse we did in Hawaii.
For sure. If folks are interested in using Orleans, maybe just to try and experiment with it to see what it's like, or actually adopting it, where would they go to try that out? So is it on GitHub? Is that?
Yeah, so just go to GitHub and search for Orleans. You'll find it there. We also have the Gitter chat, and the link is there. That's where the community hands out, and that sort of gives a lot of energy to my team when they go and talk with those people in real time and answer their questions and hear their ideas, their feedback. So kind of feedback comes in form of issues and comments and issues on GitHub, but at the same time there's real-time, near real-time chat where people just come and say. And oftentimes people come and say, oh, thank you for what you're doing and what can be better.
Yes, it's very nice.
It's kind of instant gratification.
To get that. So I guess maybe 2 last questions. One is, what are your aspirations for what you want to do with Orleans next? And then the second one is just any closing comments.
So we just had a big, first really major release in March, Orleans 2.0. The goal there was .NET core. I mean, that's standard compatibility. So now people can run literally anywhere they want on macOS, Linux, Docker containers. So it was a big deal for us, and we restructured and we matured the code base much more dependency injection friendly, and we're much more serious about backward compatibility now. And as part of that, we introduced beta of transactions, which keeps blowing people's mind when they distribute transactions that they're completely impossible, they're slow, and we're trying to prove that no, that can actually scale and be efficient. So that's the next big thing we're finalizing. We have beta that's working, but we want to finish it. We're working with internal team that does virtual commerce for gaming to productize it.
Right. Make sure you take the right amount of money in one account and put it in another kind of thing.
Yeah, they have funny scenarios like exchanging gold coins for cannonballs, and you don't want to spend gold coins that you don't have, right? So the counting rules apply there as well.
Yeah, well, I'd be happy to spend gold coins I don't have to get your cannonballs. No problem there.
Right. In closing, I would invite everybody to GitHub, to the open source. It's a great place. Like our GitHub community, it has some people that sometimes don't even use Orleans yet in their day job. They just like the crowd of people because it seems like, in my opinion, attracts people that are kind of experienced, they're passionate. So you don't get people that just do like lazy job. They would not go there. So you have this self-selection of people that they really know what they're doing, really passionate, and they're very good to each other, helping and exchanging ideas. So I would advise everybody to go there and just check out Orleans and ask questions. It's a very friendly crowd. We're there, like my team is there.
Yeah, sounds like a wonderful community.
Yep. We very much enjoyed, so I had no problem hiring people and explain what we do.
Yes, for sure. Yeah, that's what this whole open source thing is, right? It's a hiring mechanism.
No, of course not.
No, totally
I mean,
true.
it sets the bar, right? So it's like
It
you
does.
put this code and everyone can see it, so you cannot do a sloppy job, or you try to do as best as you can, and you learn to accept feedback. It's not like first thing you'll learn is being defensive, right? Like I'm sure you guys went through that.
Oh yeah, yeah. We're not doing that. Yeah, not being defensive. Okay, awesome. Well, thanks for coming by.
Pleasure.
It's nice to see where Orleans has kind of ended up, having kind of worked with you maybe 2 years ago on this. Yeah, so take a look on GitHub. I think it's github.com/.net/Orleans, right?
That's
yeah,
correct.
that's right, because we're in the same GitHub org. So take a look. It's one of basically .NET Core's sister projects, and give it a try. And thanks for watching another episode of the On.NET Show.